So in the last lecture, we had learned the different method by which we can determine the mechanism of reaction. So in that, we had learned the kinetic studies. So by doing the kinetic experiment, you can determine the mechanism of reaction. So the kinetic studies gives a lot of information which may give the positive pathway of reaction. The rate of reaction is the rate at which the reactant disappear or the product appear at a particular time. So the rate of reaction is found by the change in a concentration, color, conductivity, and any other properties that are varies with the time. Okay, so in the last lecture we had learned the example of SN2 reaction. So in alkaline hydrolysis of primary alkyl halide, you know that the primary alkyl halide undergoes SN2 reaction. So in alkaline hydrolysis of primary alkyl halide, the rate of reaction, okay, the rate of reaction depends on only on the concentration of alkyl halide. Okay, sorry, the rate of reaction depends on both the concentration of alkyl halide and nucleophile. Okay, so this suggests that the transition state involves both alkyl halide as well as nucleophile. Okay, so so in this SN2 reaction, the alkaline hydrolysis of primary alkyl halide, the rate of reaction depends on both the concentration of alkyl halide as well as the concentration of nucleophile. Okay, so this suggests that the rate of reaction depends on both the transition concentration of alkyl halide and nucleophile. Okay, and it means that the transition state involves both your alkyl halide and nucleophile. Okay, so rate is equal to K in bracket your primary alkyl halide, that is we had taken the example, that is methyl bromide CH3Br, and in bracket OH. So rate is equal to K. So the rate is depend on both the concentration of alkyl halide as well as nucleophile. Okay, this is what we had learned in last lecture. Again, in the last lecture we had learned the alkaline hydrolysis of tertiary alkyl halide. The rate of reaction is depend on the concentration of alkyl halide, and it is independent on the concentration of nucleophile. Okay, so thus both the alkyl halide and nucleophile are not involved in the same step in a hydrolysis of tertiary alkyl halide. Okay, because the rate is independent on concentration of nucleophile. Rate is only depend on the concentration of tertiary alkyl halide. Okay, so this suggests that the transition state involves only your alkyl halide, tertiary alkyl halide. So in the last lecture we had learned its reaction and mechanism. Okay, so in first one, that is your uh, that is SL2 reaction. Order of reaction is second order, and while the sorry, what the second reaction, okay, second reaction follows SN1 pathway. Okay, and which is a first order reaction, and the first reaction means SN2. Okay, which follows SN2 mechanism, and it is a second order reaction. So this is just a revision that what we had learned in the last lecture. So students, again in the last lecture we had learned the trapping of intermediate. Okay, so you know that the sometime organic intermediates are formed during the reaction. Some organic intermediates are formed during the reaction, and they are trapped by the chemical reaction, to know their to know its existence. Okay, so this intermediate is nothing but the species that is formed during the reaction, that is called as intermediate. The species formed during the reaction, that is called as intermediates. Okay, so in the last lecture we had learned the Riemer-Tiemann reaction. Okay, so Riemer-Tiemann reaction is nothing but the reaction of activated aromatic compound, okay, in presence of chloroform and KOH. Okay, you will get the formylation of aromatic ring, okay. So in that what the Riemer-Tiemann reaction, the formation of dichlorocarbene is established as an intermediate, and we are trapping that dichlorocarbene intermediate by reacting with the double bond containing compound. Okay, so so in that reaction your CHCl3 react with KOH. Okay, so the reaction between these two molecules, it generates dichlorocarbene as the intermediate, or you can simply call as carbene as the intermediate. Then what we have to find out the existence of that intermediate, okay. So we are reacting that intermediate with the double bond containing compound. Okay, so and we'll get your cyclopropyl derivative, and from that you can say that during this Riemer-Tiemann reaction, the carbene is generated as the intermediate. Okay, so by first you are trapping the intermediate, then you are analyzing the product. Okay, and from that you can say that the reaction involves the formation of dichlorocarbene as a intermediate. Dichlorocarbene as the intermediate. Okay, so an intermediate is generally trapped by running the reaction in presence of compound with each react. Okay, so what in this method, what we are doing is that an intermediate is generally trapped by running the reaction. Okay, we are running the reaction with the compound with that intermediate is react. Okay, so this dichlorocarbene react with double bond containing compound, it forms cyclopropyl compound. Okay, and from that you can say that during this Riemer-Tiemann reaction, dichlorocarbene is generated as a intermediate. Then again we had learned the example of benzene intermediate. So benzene is intermediate. Okay, so that benzene intermediate is trapped by anthracene. Okay, by Diels-Alder reaction you will get the trypticene as a product. And from that you can say that during that reaction you are getting the benzene as the intermediate, and that benzene is immediately react with the anthracene and it form the product trypticene. Okay, by analyzing the product. Now once you get that trypticene as a product, now you can say that okay, during that reaction uh, benzene is generated as a intermediate. That's why you are getting this trypticene as a product. Okay. Then again we have learned the what carbocation intermediate. Okay, so you know that in this carbocation the nucleophile are used to trap the carbocation. So different mixture of nucleophiles we are using to trap the carbocation. So this is the direct evidence that the addition of halogen to alkene proceeds through the formation of carbocation intermediate, and it is obtained by performing the reaction in presence of other nucleophile. Okay, and when the mixture of products are obtained, okay, and from that you can say that during this reaction, okay, your carbocation is generated as an intermediate because you are getting the mixture of product. So you are using different nucleophile. Okay, different mixture of nucleophile, and you are getting the mixture of product. So from that you can say that during that reaction, okay, your carbocation is generated as a intermediate. Okay, so this is the just revision. Okay, again in the last lecture we had done one trapping of radical intermediate. Okay, so IIBN in presence of light or heat undergoes homolysis. So breaking of that your sigma bond takes place, homolysis of sigma bond takes place, and it generates the radical. Then to trap that radical we are using nitric oxide. Okay, and you will get the product. Okay, so by analyzing that product, okay, you can say that during this reaction what radical is generated as a intermediate. Okay, so you know that the intermediates are short-lived species. short-lived species, and they are formed during the reaction. Okay, they are immediately react, or they are immediately convert into product. Okay, so an intermediate is generally they are short-lived species. Okay, that's why we are trapping by running the reaction in presence of compound with which it react. Okay, so there are different compounds are there, with that your intermediates are reacting. Okay, and then after that, once they react, okay, you will get the product, and by analyzing the product we can determine, we can say that during that reaction this or so intermediate is generated. Okay, so this is the just a revision that what we had done in the last lecture. Now student, today I am going to teach you the experiment crossover experiment. Crossover. Oh, C6 Al L3 H5, you will get this product. Okay, so let's label this. Then second reaction, CH3. Okay, AlCl3, and after rearrangement, second. Okay, first reactant, second reactant similarly constituted but non-identical. This will give you this product. Okay, after Fries rearrangement, okay, in Fries rearrangement, this AlCl3, it's your Lewis acid. Okay, this OH low oxygen lone pair will form coordinate bond with this AlCl3. Okay, and the breaking of this OC bond takes place, and this COC6H5, this group will migrate from oxygen to the ortho carbon of this phenyl ring. It will join to this, and then the keto-enol tautomerism, in a keto form changes to enol. Enol is the most stable. Okay, same here, this is your second reactant. Okay, here same, this AlCl3 react with this phenyl ester, and rearrangement takes place. Rearrangement reaction takes place, breaking of this OC bond. This C double bond OCH3 group migrate from this oxygen, and it will join on this carbon. Okay, and you will get this product. So this is your product number first, product number this is your reactant first, reactant second. Okay, and we are labeling fifth, third and fourth. Okay, so this is the product of your first reaction, this is the product of your second reaction. Okay, now what we are doing, we are doing the reaction. Okay, we are doing the reaction by taking the mixture of this first and second. So this is your first, second, OH, CH3, let's label. This is your sixth one, fifth and sixth one. Now you are doing the crossover experiment. You are doing the reaction of two similarly constituted but non-identical reactant, okay, and you are getting this four different product, okay, four different mixture product. And once you get this product, you are analyzing that, and by analyzing this product, you do what, you say that you are getting the mixture of product, okay. Now you can say that this Fries rearrangement, it's a two-step reaction, Fries rearrangement, it's a two-step reaction, and it is a what, intermolecular reaction, okay. So intermolecular reaction, because in intermolecular reaction, first the breaking of this fragment takes place, okay, then this fragment separates from the reactant, and then what, then it, in second step, it join to the phenyl carbon, okay, it joins to phenyl carbon, okay. Once it separate from first this fragment, okay, it can join to this what, it can join with the second reactant also, okay. And from that you can say that this reaction, it is a two-step reaction, and it is a intermolecular reaction, okay. Rearrangement is intermolecular rearrangement is intermolecular rearrangement, because you are getting the mixture of product, okay. So if two different phenyl ester are subjected to Fries rearrangement, these are the two different phenyl esters are subjected to Fries rearrangement, then four products are obtained, 1 2 3 4, four products are obtained, formation of this cross product, okay. For first, the for this your product number third and product number fourth, okay. These are the products of intramolecular rearrangement, okay, molecular rearrangement within the molecule, okay. And this is due to these two are the crossover product, this is due to crossing of this fragment from one molecule to another molecule, crossing of one molecule from one molecule to another molecule, okay. So here the migrating group must become free in a two-step process, okay. So this Fries rearrangement, it is a two-step process, and this migrating group, that is C double CO C6H5 CO CS3, okay. Migrating group must become free in a two-step process, and we should get the product containing the fragment of both the reactant, okay. Here we are getting the product, what we are getting the product containing the fragment of both the reactant, okay. So here this is your COC6H5, okay. Now this COC6H5 join to this second reactant, okay. So this is the product of that crossover, this is your crossover product Cl, this is your COC6H5, this fragment, okay. What this COC6H5. This is your COC6H5. And let me change C6 oxygen. CH3. Okay, so these are the starting material for the Claisen rearrangement. Allyl phenyl ether. Okay, so these are the similarly constituted but non identical Okay, so we are doing the reaction of this mixture of two reactant plus. So this is your first product, and the second one is so these are the two products that you are getting after doing this Claisen rearrangement. Okay, so here you are not getting the crossover product. Okay, so this molecule after rearrangement, okay, so ortho position is blocked, so this group will migrate here. Okay, this group will migrate on this para carbon, and you will get this product. Same here, this bond will break. Okay, So and this CH2 CH double bond, this group will migrate and it will join on this carbon. So here you are not getting the mixture of product, you are not getting the mixture of product, or you can say that you are not getting crossover product. Okay, so you are doing the reaction of two similarly constituted but non-identical reactant. Okay, and you know that if you are getting the crossover product, then that reaction is intramolecular, then that reaction is intermolecular. So here you are not getting the crossover product, you are not getting the crossover product or a cross product. So you can say that this reaction, it is a, the reaction involves this reaction, this rearrangement, it is a intramolecular rearrangement. Rearrangement is a intramolecular rearrangement, because you are not getting the crossover product, you are not getting the crossover product. Okay, so here in this reaction, this what this group will directly migrate from this to this carbon. Okay, and the reaction, it is a intramolecular rearrangement, the rearrangement within the molecule, rearrangement within the molecule, that is called as intramolecular rearrangement. Okay, so by doing this crossover experiment, you can easily find out whether the rearrangement is a intra or a intermolecular. Okay, in the first reaction, that is the Fries rearrangement, you are getting the mixture of product, you are reacting to reactant and you are getting four different product, you are getting four different product, and two products are due to crossover, the crossing of one fragment from one molecule to another molecule. Okay, so that Fries rearrangement, it is a intermolecular rearrangement and it is a two-step reaction, it is a two-step reaction. While this one, okay, Claisen rearrangement, it is a intramolecular rearrangement, it is a intramolecular rearrangement, and it is a one-step reaction, it is one-step reaction, because in this reaction you are not getting cross product, you are not getting cross product, you are not getting cross product. Okay, so this is about your crossover experiment. Any doubt regarding this? Hello? Yes. Yes, Omkar. ओमकार बोर्लेकर, विशाखा पाटील, भावना बोर्लेकर, मंगेश निरगुडे, विशाखा पाटील, आरती यादव, अक्षय, अर्चना मुलिक, बारकू पाटील. Hello. Ah, okay, so what did you understand from this crossover experiment? Explain explain me in a short, what did you understand from this crossover experiment? Yes, Bhagat Saili, Darshan Patil, Jyoti Sharke. Yes, so what is meant by crossover experiment and what is the use of this experiment, crossover experiment? Krishna Shelke, Madhumita Joshi, Mahesh. So what is meant by crossover experiment? By doing the crossover experiment, okay, can you determine the mechanism of reaction? Yes. So this Fry's rearrangement, okay, Fry's rearrangement, whether it is one step or two step reaction. Two step react. Okay. So in a crossover experiment, what you are doing? Tell me in a short. What you are doing in a crossover experiment? Okay. So uh, simply काय माहिती आहे का? Okay. So what we are doing this crossover experiment. Okay. Two similarly constructed but non-identical reactant. If you are getting crossover product, जर तुम्हाला crossover product भेटत असतील, then that reaction is a two step reaction. म्हणजे ती reaction two step reaction असणार. आणि that rearrangement or that reaction, it is a intermolecular reaction. It is a intermolecular reaction. Okay, or you can say that the intermolecular rearrangement within the two different molecule. Rearrangement within the two different molecule. Okay, so if the crossover products are formed, then that reaction or the rearrangement, it is a intermolecular rearrangement. If the crossover products are not formed, then that is intramolecular. That is intramolecular rearrangement, and that intramolecular rearrangement are one step reaction. Okay, so in one step reaction there is no chance of formation of cross product. In intra there is no, because that rearrangement is within the molecule. That rearrangement is within the molecule, because what, the rearrangement takes place within the molecule, so there is no chance of formation of cross product. Okay, and it is a one step reaction. सगळं काय ते एका स्टेप मध्ये होतं, बरोबर. त्याच्यामुळे तुम्हाला क्रॉस ओव्हर प्रोडक्ट भेटत नाही. आणि जे टू स्टेप रिॲक्शन असते, टू स्टेप रिॲक्शन, फॉर एक्झाम्पल फ्राईज रेजमेंट, इट इज अ टू स्टेप रिॲक्शन. पहिली स्टेप मध्ये तुमचा तो ईस्टर बॉन्ड ब्रेक होईल, ऑक्सिजन कार्बन, देन दॅट part will migrate from one reactant of first molecule to the reactant of a second fragment. दुसऱ्या फ्रॅगमेंटच्या रिॲक्टंट सोबत तो दुसऱ्या रिॲक्टंटच्या फ्रॅगमेंट सोबत तो रिॲक्शन होईल. दॅट इज ए टू स्टेप रिॲक्शन. ओके, so to find out whether the reaction is two step or one step, or whether the rearrangement is intra or intermolecular, we are doing this crossover experiment. We are doing this crossover experiment. ठीक है. Any doubt? मृणाली माली, नेहा ससाने, पायल, पूनम मागलावे, प्रमोद सावंत, प्रणय पाटील, प्रताप सरकते, प्रतिभा शुक्ला, राहुल कदम, राठौड़ प्रियंका, रेणु मिश्रा, रेणु सेनानी, रुद्रतेज. यस, एनी डाउट? हो, सगळं समजलंय. ठीक है. Now let's move towards the next point. Move towards the next point. That is stereochemical evidences. Stereochemical evidences. Okay. Stereochemical evidences. Stereochemical evidences. Okay, so mechanism of nucleophilic substitution reaction can be investigated by carrying out the experiment of optically active compound and the checking the optical activity of the product. Okay, so in stereochemical evidences, okay, what you are doing is that, okay, the reaction of nucleophilic substitution reaction, you are doing the reaction of optically active compound. You are doing the reaction of optically active compound, the molecule that rotates the plane polarized light, the molecule that rotates the plane polarized light. Okay, and you are, after completing the experiment, again you are checking the optical activity of a product, okay. If the if the product is optically active, okay, then you can say that reaction involves the inversion of configuration. Because your starting material is optically active and your product is also optically active. Your whatever the reactant you are using, you are doing the reaction of optically active compound, that your reactant is optically active, and you are getting the product, and that product also has the optical activity. Okay, and you are checking the optical activity of that product, and you can say that reaction involves the inversion of configuration. So here you can simply say that, okay, in inversion of configuration, it might the SN2 reaction takes place, the backside attack of nucleophile takes place. That's why there is a change in the configuration, or you can say that there is a inversion of configuration. Okay, because your product also having optical activity. So this is your one case, and another case is your starting material is optically active, or you can say that your reactant is optically active, and your product is optically inactive. So here you can say that this nucleophilic substitution reaction, okay, this reaction involves the racemization of product. And nucleophilic substitution reaction takes place via SN1 mechanism. So this is the just overall about your stereochemical evidences. So I will take the example, so you can easily get the detailed understanding of stereochemical evidences. So mechanism of nucleophilic substitution reaction can be investigated by carrying out the experiment with optically active compound and then checking the optical activity of the product. And you are checking the optical activity of a product. Racemization of the product shows the formation of planar intermediate. Racemization of the product shows that the formation of planar intermediate, such as carbocation, which is equally likely to be attacked by the nucleophile on either side and yielding the mixture of equal number of molecules with retention and inversion of configuration. Okay, thus the stereochemical evidences indicate that the following mechanism for SN1 reaction of alkyl halide is, okay. So let's take example of one reaction. So this is your tertiary alkyl halide, H5 C2H5, CH3, H7, okay, C3H7. So this is your tertiary alkyl halide, okay. Hydrolysis of this tertiary alkyl halide takes place, okay. So first step is ionization of this CBr bond. First step is ionization of this CBr bond. CBr bond takes place, okay. So this CBr bond, it is a polar bond due to inductive effect, because this bromine is more electronegative than carbon, okay. So hydrolysis of this CBr bond takes place. This Br leave, you know that this is your sigma bond, and it is what one electron shared by this carbon and one electron shared by this bromine, okay. So the heterolysis of this bond takes place, and there is it generate positive charge on this carbon and negative charge on this bromine. You will get planar intermediate. You will get the planar intermediate. Get the planar intermediate C2, C3, CH3, okay, CH3. So this is your starting material, okay. The starting material is optically active, because this starting material having chiral carbon, okay. The carbon which is attached to 4 different group, and this starting material is optically active, okay. So by first step is ionization, you are getting this intermediate carbocation as the intermediate, carbocation as a intermediate. Now on this carbocation, this is your planar intermediate. Your nucleophile. Your nucleophile can attack from both the sides. So this is your OH minus, it can attack from both the side, top side as well as bottom side. So it attacks from top side, and it can also attack from OH. Here you are getting a racemic mixture, okay. So your starting material or the reactant, it is optically active. And you are doing the reaction, and after that, once you get this product, so this is your product, okay. This is your product, and you are checking the optical activity of this product, okay. And your product is optically inactive. Okay. So you can say that this reaction, or you can say that the reaction of this, or the hydrolysis of this tertiary alkyl halide, it follows SN1 pathway. SN1 pathways, because in SN1 pathways there is a formation of planar intermediate. That is carbocation, and that carbocation, okay. So that carbocation can attack by nucleophile from both the side, top side as well as bottom side. It having 50-50% possibility, okay. So that's why suppose your starting material is R, okay, so you are getting in product, you are getting 50% R and 50% S, 50% R and 50% S. So you are getting the mixture product, you are getting the mixture product, and you know that that is called as racemic mixture. 50% R and 50% S, it is a racemic mixture. It is nothing but the equimolar mixture of two enantiomer. It is nothing but the equimolar mixture of two enantiomer. Equimolar mixture of two enantiomer, and this racemic mixture is optically inactive. Racemic mixture is optically inactive because what? Because one enantiomer rotates the light on right hand side and one rotate on left hand side, okay, and the net effect is zero. Net effect is zero. That's why the racemic mixture are optically active, okay. So by doing this experiment, by doing this method, that is stereochemical evidences, by finding the stereochemical evidences, you can easily determine the mechanism of reaction. So the method simply involves checking the optical activity of starting material as well as product, okay, and from that you can easily say that and this is only limited for nucleophilic substitution reaction, okay. This method is only applicable for nucleophilic substitution reaction, okay. So in this method you are checking the optical activity of a starting material as well as product, okay. If your starting material is optically active and you are getting optically inactive product, okay, so this reaction, the product is CH, H, CH3H. So product having P reaction with Br2, okay, you will get you will get trans dibromo product, trans dibromo product. So by analyzing the product, you can determine whether the reaction it is a one step or a two-step reaction, okay. So addition of this Br2 to this cyclopentene, you will get this trans product, you will get this trans dibromo, positive charge on bromine, cyclic bromonium ion intermediate. You will get this cyclic bromonium ion intermediate. Now this another Br attack from bottom side, okay, and it opens the ring. That's why you are getting trans product. So by analyzing the product, also if you are getting the trans product, then you can say that this reaction it is a two-step reaction. So the addition of bromine to carbon carbon double bond, okay, it is a two-step reaction. First there is a formation of cyclic bromonium ion intermediate, then another Br attack from bottom side and it opens the ring. That's why you are getting trans product. So it is a two-step process. And another example is what your formation of diol, that is osmium tetroxide, and with KMnO4 it is a simply one step reaction. Okay, a double bond react with KMnO4 or osmium tetroxide, you will get diol as a product. So that is the example of one step or a single step reaction. While this addition of Br2 to this carbon carbon double bond, okay, or a cyclopentene gives trans dibromo product, gives trans dibromo product. So the direct one step addition of Br2 actually gives cis dibromide product. Okay, direct addition will use cis product, but this is not a direct addition. This is not a direct addition. First, what, that Br molecule react with cyclo over your double bond, okay, and it generate carbocation. Then that carbocation, you are having bromine have a lone pair that will attack on that carbocation, and it generates cyclic bromonium iron intermediate. You will get what, this type of intermediate. Then another Br molecule attack backside or attack from bottom side, and it opens the ring, that's why here you are getting this trans product. Okay, so it is not a direct addition, okay. So so you can say that by analyzing the product you can determine the mechanism of reaction, or you can say that this reaction involves, it is a two-step reaction, okay. While single step reaction, that is your addition of Br2, addition of reaction of KMnO4 or osmium tetroxide with a double bond, you will get diol as a product, and that is the example of one step reaction. Because in that reaction you are getting cis product, okay, while here you are getting trans product. So trans product, two step reaction, cis product, one step reaction, and only two reagent will give one step reaction, that is your osmium tetroxide and KMnO4, okay, that you are using in your qualitative experiment, okay, to determine the presence of saturation or unsaturation, to determine whether your compound having carbon carbon double bond or carbon carbon triple bond. Okay, so just you are adding some amount of KMnO4. If the color of KMnO4 changes from pink to colorless, then you can say that unsaturation is present. If there is no change in a KMnO4 color, then you can say that the saturated compounds are present, because you know that only compound having double bond will react with KMnO4. It is a simply single step reaction, and you will get diol as a product, that is cis diol. You will get cis diol. So this is about the stereochemical evidences. Any doubt regarding this? Yes. हेलो. करे समझ लगा रहे. हेलो. Hello. Hello. Yes. Any doubt? Okay, now you can leave the class. Yes.